Advanced mode for fancy color diamonds. Analysis of fancy color diamonds is one of the most complicated tasks in the gemological laboratory. The value of these stones is so high that a huge wealth of resources are today invested in the development of treatments and synthetics. Besides classical gemological methods, it involves a number of spectroscopic techniques which, in some cases, can be sometimes inconclusive. This is the reason why we should consider each color as a separate issue. For some of them, fluorescence spectroscopy can be conclusive. For some others, it can only provide for an element which needs to be integrated with the clues gathered from other specific techniques. In this video, we will cover only the colors for which the EXA can give effective results. Natural pink diamonds. The vast majority of the fancy pinks on the market nowadays are type 1 AAB. This means that their spectra will not differ from the most common ones featured by the highest percentage of colorless diamonds. Entry peak at 415 nanometers is present, along with its side bands, and their fluorescence is of course blue. HPHT synthetic pink. HPHT synthetic pinks are type 2A, where irradiation and annealing processes make a minimum quantity of isolated nitrogen to bond with vacancies in creating the NV centers at 575 and 637 nanometer. The negatively charged NV center at 575 nanometers is indeed responsible for generating the pink color, and the fluorescence reaction of these diamonds is generally orange. CVD synthetic pink. CVD pinks are not very much different from the HPHT. They have very similar spectrum and fluorescence reaction. The silicon vacancy peak, which could lead to their identification as CVDs, is almost always too weak comparing to the emission due to the NV centers to be seen. Either HPHT and CVD synthetic pinks display generally high saturated colors. Natural irradiated and annealed pink. This process requires a very specific and rare type of natural diamond. Low nitrogen type 1AA plus 1B may exhibit brownish, greenish, unattractive colors, and they are the perfect candidate to become beautiful, highly saturated purplish pink. The irradiation generates vacancies in the crystal lattice, and the annealing allows them to bond to the isolated nitrogen. This results in the creation of the negatively charged defect NV at 575 nanometers, producing a very attractive and rather unique purplish pink color. Natural multi-treated pink. These diamonds are the natural evolution of the simply irradiated and annealed one, and came to the market only after the HPHT process has been developed and refined for the task. They are natural type 1 AAB and are carefully sorted by their low nitrogen aggregates content to be good candidates for becoming nice pink diamonds. A multi-step process including HPHT, irradiation and annealing treatments is carried out. As it happens for the synthetic pinks, the NV centers are generated to produce the pink color. The fluorescence spectrum shows the N3 and its side bands, plus the NV bands, very often combined with H3 band in green. The fluorescence emission features an interesting orange-green-blue patchy pattern. This spectrum is highly diagnostic. Golconda pink. Although extremely rare, natural 2A pink diamonds colored by the NV centers, the same cause of the color in the synthetic pinks, do exist. Known as Golconda pinks, usually they are not much saturated. This occurrence should be taken into consideration when evaluating the fluorescence spectrum before to claim the stone is synthetic or treated. Natural coated pink. There are few companies producing coated fancy color diamonds, especially in the melee size. The coating is applied on the pavilion only, but it's almost impossible to notice, especially when they are set in jewelry. The EXA is not able to spot for coatings, so the spectrum will be identical to the one of a natural 1AAB pink diamond. It's highly suggested to carefully observe pink melee diamonds at high magnification. A diagnostic abrasion pattern on the facet junction of the pavilion is almost always present and can be revealed even more easily when the EXA beam is used in combination with a microscope, like in this case. Assembled stones can give the same reaction. It's always advisable to watch closely if the fluorescence emission is coming from the whole stone or from only a part of it. Natural blue diamonds. Natural blue diamonds are almost always totally inert to the standard long-wave UV lamps. The concentrated beam of the EXA can sometimes stimulate a weak reaction, like in this case, but very often their spectra show nothing but noise. Here you can see the GR1 peak at 741 nanometers, which is not uncommon in natural untreated type 2 diamonds, and it disclosed naturally occurring vacancies in the crystal lattice of this highly stressed material. CVD Blue Diamond. CVD blue diamonds are usually type 2A submitted to a post-growth irradiation. The fluorescence is usually weak, chalky greenish blue, and the spectrum features the distinct GR1 band at 741 nanometers, in this case diagnostic of irradiation. Unfortunately, the silicon vacancy band at 737 nanometers is too close to the GR1 to be distinguished at room temperature. HPHT Blue Diamond. HPHT synthetic blue diamonds are usually type 2B and are not possible to be distinguished from natural by fluorescence spectroscopy. Natural irradiated blue. These are the most common blue diamonds on the market. Usually type 1 AAB, treated by irradiation to generate the blue color. The fluorescence color is often a weak chalky whitish blue, and the spectrum is highly diagnostic of a non-natural blue, which are type 2B, since the N3 and sidebands are present, along with the GR1 indicating the irradiation. Notice the extent of the GR1, which is usually higher in artificially irradiated material than in natural blue stones. After watching all these stones and their reactions, you should start to understand the complexity of dealing with fancy colored diamonds. And by the way, we discussed only 2 colors, and the ones which requires less efforts than others. Multi-step treatments and synthetics are the real challenge today. Science allows to really get an ugly frog and after a number of steps to turn it into a beautiful prince. Fluorescence spectroscopy can be very useful, sometimes diagnostic, but in most of the cases it provides only for a piece to solve such a complicated puzzle.
Thank you for watching this video. For more information about our spectrometers, please visit our website. And if you have any question, please don't hesitate to contact us at info@gemoraman.com.